Next, we discuss the shape of the distribution. The two basic properties that describe the shape of the distribution are scale and skewness. The standard deviation is usually used to describe the scale of a symmetric distribution, but its interpretation tends to break down when used to describe a highly asymmetric distribution or a heavy-tail distribution. Skewness, on the other hand, is usually computed using cubic function of data points deviations from the mean. Although it has been used to describe the non-normality of a distribution, we need more methods that could link skewness to a predictor variable. In QRM, we may quantify both scale and skewness using quantiles. QRM and shapeshifts. Recall that in OLS, we assume a location shift model, wherein the conditional mean distribution of the response variable depends on the predictors. For the normal error model, we assume that the error terms are independent, normally distributed, and homoscedastic. In matrix rotation, recall that Y follows an n-variate normal distribution with mean vector x beta and variance-covariance matrix sigma squared I. In this case, the conditional mean distribution of the variable y depends on the predictors. Meanwhile, we can see that the variances of y are constant because of sigma squared I, and this is a consequence of our assumptions that we have a normal error model. A graph of a homogeneous error model with normal errors is shown in the left. In this model, we only have a single predictor variable x. So the red dashed lines show the plotted estimated regression equation. Meanwhile, the blue lines are the plots of the estimated quantiles of y at several values of p. Graphically, we can see that the slopes of the conditional mean fit and the conditional quantile fits are parallel. The values of beta 1 hat from OLS and the values of beta 1 hat p for the various quantiles are more or less the same. This is an indication of a location shift model. Also notice from the scatter plot that the points seem to be contained in the graphs of the parallel lines. In social science research, it is often the case that the conditional distribution of the response variable manifests shapeshifts, or the change in scale and/or skewness. Besides a shift in location, a unit change in the predictor variable can also change the shape of the response distribution. So, quantile regression could show information on the location and shape of the conditional distribution of the response variable. In this part, we will see one advantage that QRM has over OLS. Take a look at our graph in the left side. Again, the red dashed lines show the plotted estimated regression equation, while the blue lines are the plots of the estimated quantiles of y at several values of p. Notice that the slopes of the lines are not parallel. Also notice that the lines seem to be funneling. Also, again, notice that the points in the plot seem to scatter as we increase the value of our predictor variable x. So this is a classic example of a location and scale shift model, where there is an increase in the scale of the conditional distribution of y for a unit increase in x.